Hey, welcome back. We just finished electrostatics, and now we are going to turn our attention to magnetostatics. Before we do that, I want to summarize how we got here and also summarize Maxwell's equations yet again. These are Maxwell's equations in or most general form. E is the electric field intensity, as you now know. H is the magnetic field intensity, which we have not said anything about. Now, in the static case, or I guess in the general case, before we get to the statics case, in the general case, the four equations I have here, you see you cannot separate the magnetic field intensity H from the electric field intensity E based on the middle two equations. You see the curl of E is related to H and the curl of H is related to E. However, if you assume a static field, so E is not changing with respect to time, right? The charges are static, or H, the magnetic field, is not changing with respect to time, then the first equation, well, the first equation is just as is, right? And based on the relationship between the electric field intensity and the electric flux density, we could alternatively write this like this. Okay, the second equation then in the static case would say that the curl of E is equal to 0, or the curl of D is equal to 0. So we talked about this, right? We talked about these equations. And now you'll notice then equation 3 is that the curl of H would be a constant. And then you would see that the divergence of H, well, that one doesn't change. That's equal to 0. But the point is that if you assume the static case where the fields are not changing with respect to time, now you can separate them out into electrostatics, the first two equations, which we now understand, and the last two equations, the third and the fourth equations, which we will work on understanding now in the course. Now, if you remember, for electrostatics, we didn't just go right into these top two Maxwell's equations. We started with Coulomb's law, and then from there we went to Gauss's law, which is one of these equations, and then we talked about the other, and so that's how we got to the electrostatic equations. With magnetostatic equations, the last two equations there, we're going to do something similar. We're not going to jump into these two equations at first. We're going to first learn the Biot-Savart law, which is analogous to the Coulomb's law for electrostatics. And then from after the Biot-Savart law, we're going to go into Ampere's law, which is like Gauss's law but for magnetostatics. So we're going to work on those two equations, and then we're going to come back to the Maxwell's equations for static fields. So that's where we're headed. And I'd just like to say again, just like the electric force, the magnetic force, they're actually the same thing, electromagnetic force. It's fundamental in nature, and it's not broken down any further. So we're not going to explain what it is, what is the magnetic field. We're going to explain its properties, how it behaves, and what creates it, and so forth. Just like for gravity, gravity is a fundamental force. We don't explain what it is in physics. We can just tell you what makes the force and how it behaves. Okay, so next up then is the Biot-Savart law. So I claim that that is the analogous situation to Coulomb's law. So what is the Biot-Savart law and how does it work? That's coming at you in the next video. Thank you.